If the researcher isn't able to make a confident prediction ahead of time about whether the correlation will be a positive correlation or a negative correlation, then the person will use a two-tailed test. So if the person isn't able to make a confident prediction before collecting the data about whether the correlation will be positive or negative, the person will use a two-tailed test. In class, we talked about how the correlation between number of children and the number of hours a person works per week could be a positive correlation or a negative correlation, because it could be that people who have more children tend to work more hours per week because they need to support their children, but it could also be that people who have more children tend to work fewer hours per week because they need more time off to take care of their children. So if we were doing a study on the correlation between the number of children a person has and the number of hours a person works per week, it would probably be difficult for us to predict ahead of time whether we would find a negative correlation or a positive correlation, because both types of correlations seem to make sense. And since we wouldn't be able to confidently predict ahead of time whether the correlation between number of children and hours worked per week is positive or negative, we would use a two-tailed test in that study. In a two-tailed test, the null hypothesis, which is HO, says that there's no correlation in the population, and the alternative hypothesis, which is H1, says that there's a correlation in the population. The alternative hypothesis doesn't say whether the correlation is positive or negative. It just says that there is some type of correlation in the population. So if we were doing a study on number of children and hours worked per week, and we were doing the two-tailed test, our null hypothesis would say that there's no correlation between number of children and hours worked per week in the population, and the alternative hypothesis would say that there is a correlation between number of children and hours worked per week in the population. Our alternative hypothesis wouldn't say whether it's positive or negative. It would just say that there is a correlation between between number of children and hours worked per week. And in a two-tailed test, both the negative and the positive critical values are used. You have a negative critical value at the left end of the number line, and a positive critical value at the right end of the number line. And the entire p-value is used. I'll explain what that means. So far in class, we've been talking about the two-tailed test. We haven't been talking about the other types of tests yet. So that's why I started talking about the two-tailed test first. And I'll show you a picture of what the two-tailed test looks like. In a two-tailed test, you have the negative critical value at the left end of the number line, and the positive, I'm sorry, that's not the critical value. You have the negative critical value at the left end of the number line right here, where this red area starts. And you have the positive critical value at the right end of the number line, where this red area starts. And the area starting at the negative critical value and going out to the left is the negative rejection region. And the area starting at the positive critical value and going out to the right this way is the positive rejection region. If your outcome, if your sample correlation coefficient lands in the negative rejection region, you reject the null hypothesis of no correlation, and you conclude that there appears to be a negative correlation in the population. If your outcome, meaning your sample correlation coefficient, lands in the positive rejection region, you reject the null hypothesis of no correlation, and you conclude that there appears to be a positive correlation in the population. And if your sample correlation coefficient lands in between the two critical values in the middle area, you give the null hypothesis the benefit of the doubt, and you just say that there isn't strong enough evidence to conclude that the correlation is positive or negative, there isn't really strong enough evidence for any type of correlation in the population if it lands in this area. And in a two-tailed test, the p-value is the area under this curve starting at your outcome, the correlation that you found, and going out to the end of the curve, combined with the area starting at the opposite of your outcome and going out to the other end of the curve. So this is the sample correlation coefficient that I'm calculating with my data set. My p-value would be the total area under the curve, starting here and going out this way, starting at my outcome and going out this way, combined with the area starting at the opposite of my outcome and going out this way. So if the correlation coefficient that I've calculated with my data set turns out to be 0.45, the p-value would be the area under the curve going from 0.45 out here to 1, combined with the area starting at negative 0.45, the opposite, and going out to negative 1 at this end. So if this is my outcome right here, of 0.45, my p-value would be the total of this green area and this green area. My p-value would be the total of the two green areas, and that's the way it is in a two-tailed test. In a two-tailed test, you have half of the p-value out here and half of the p-value out here. Now, what happens in a test that's not two-tailed? We'll cover the next type of test now, which is a left-tailed test. A left-tailed test is used when a researcher is able to confidently predict ahead of time that the correlation in the population is negative and not positive. So if the researcher is able to confidently predict ahead of time that the correlation is negative, meaning before the data is even collected, the researcher is able to confidently predict that the correlation is negative, the researcher can do a left-tailed test. And in a left-tailed test, the null hypothesis still says that there's no correlation in the population, but the alternative hypothesis is more specific. Instead of just saying that there's a correlation in the population like it does in a two-tailed test, in a left-tailed test, the alternative hypothesis says that there's a negative correlation in the population. So in a left-tailed test, the researcher is reasonably confident that the correlation is negative, and not positive. So in a left-tailed test, these are the two competing possibilities that the researcher is considering. The researcher is trying to decide between these two possibilities. And in a left-tailed test, only the negative critical value is used, and only the left one-half of the p-value is used. And I'll show you what I mean by that. So in a left-tailed test, the researcher is reasonably confident that the sample correlation coefficient will end up falling between 0 and negative 1 at the left end of the number line. And the researcher looks up the negative critical value, which will be right here, and the researcher is only using the negative critical value in a left-tailed test. There's no positive critical value. And the area going from this critical value here, out here, to negative 1 is the negative rejection region. So in a left-tailed test, all you have is a negative critical value and a negative rejection region. You don't have the positive critical value and the positive rejection region out here. So in a left-tailed test, if the sample correlation coefficient, meaning the outcome, lands in the negative rejection region, you reject the null hypothesis and conclude that there appears to be a negative correlation in the population, just like you would in a two-tailed test. And if the outcome doesn't land in the rejection region, if it lands somewhere in here, you fail to reject the null hypothesis, meaning you give the null hypothesis the benefit of the doubt. Because this is the non-rejection region in the left tail test. Also, in a left tail test, when the person calculates the p-value only includes the left half of the p-value. So in a left tail test, the p-value is just the area starting at the researcher's outcome and going out to the left end of the curve. It's this green area. It doesn't include the other half of the p-value at the right end of the curve. So in the left tail test, the p-value is only half as large as it would be in a two-tail test. And you might be wondering, what's the point of using a left tail test? Well, in a two-tail test, these two rejection regions are each equal to 0.025. So that's 0.025 is the size of this rejection region, and 0.025 is the size of this rejection region. And they both add up to 0.05. In any type of hypothesis test, you don't want the total rejection region to be any bigger than 0.05. You want the total rejection region to equal 0.05, meaning you want the total of these areas to be 0.05, and you don't want it to be any bigger than that, because if the total of the rejection regions is any bigger than 0.05, it becomes too easy to reject the null hypothesis. So I wouldn't be allowed to move this critical value out this way, or move this critical value out this way, because then the two red areas would become larger, and the total rejection region would be bigger than 0.05, and I don't want it to be any bigger than 0.05, because it becomes too easy to reject the null hypothesis. In a left tail test, what I'm doing is I'm taking the total rejection region of 0.05 and putting it all at the left end of the curve. So see where it says 0.05? So this rejection region in a left tail test is actually twice as big as this rejection region in a two-tail test, because if you add the size of this area with the size of this area, meaning if you combine these two areas together from the two-tail test, they actually equal this area in a left tail test. So the size of this red area plus the size of this red area equals the size of this red area in the left tail test. The entire 0.05 area is at the left end of the curve. And when you do that, when you move the total rejection region to the left end of the curve, it actually becomes easier to reject the null hypothesis. Because since the red area is bigger, the critical value is moving closer to 0 than it would be in a two-tailed test. Because the red area is getting bigger, and the critical value, which is the starting point of the red area, is moving closer to 0, which means that the critical value is easier to reach in a left-tailed test. So if you're reasonably confident that the correlation in the population is negative, and you're reasonably sure it can't be positive, then you could use a left-tailed test. And you have a critical value, it's easier to reach. Now what about a right-tailed test? The right-tailed test is just the opposite of the left-tailed test. If a researcher is reasonably confident ahead of time that the correlation is a positive correlation and not negative, the person will use a right-tailed test. And in a right-tailed test, the null hypothesis still says no correlation in the population, and the alternative hypothesis now says that there's a positive correlation in the population. So just like in the left-tailed test, the alternative hypothesis in the right-tailed test is more specific, because in a two-tailed test, all the alternative says that there is some type of correlation in the population. But in a right-tailed test, it's more specific and says that there's a positive correlation in the population. So in a right-tailed test, these are the two competing possibilities that the researcher is considering. The researcher is trying to decide between these two possibilities. And in a right-tailed test, only the positive critical value is used, and only the right one-half of the p-value is used. So let's take a look at what that would look like. In a right-tailed test, the researcher is reasonably sure that the outcome, meaning the sample correlation coefficient, will land somewhere between 0 and positive 1 in this area. And the researcher looks up the positive critical value from the table and uses it right here. And that critical value is the starting point of the positive rejection region. But in a right-tailed test, there's no negative critical value and there's no negative rejection region, because you're only looking at the right half of the curve. And if your outcome falls in the positive rejection region, you reject the null hypothesis of no correlation, and you conclude that there appears to be a positive correlation in the population. And if your outcome lands out here somewhere, and it doesn't reach the critical value, you fail to reject the null hypothesis, and you give the null hypothesis the benefit of the doubt. So this is the non-rejection region of a right-tailed test. And in a right-tailed test, you're taking the total size of the two red areas from the two-tailed test and putting that total rejection region at the right end of the curve. So this is actually, the size of this area is actually 0.05. It's the total size of these two areas. So you're taking the total rejection region that you're allowed to have and putting it all at the right end of the curve. And just like in the left-tailed test, that makes the critical value easier to reach. Because when this red area becomes bigger, since it's twice the size of what it was over here, the critical value is moving closer to 0, and it's easier to reach. So it's easier to reject the null hypothesis in a right-tailed test. Because remember that this rejection region is twice the size of this rejection region out here from the two-tailed test, which means that the critical value is moving in closer to 0, and it's easier to reach. So if you're reasonably confident ahead of time that you'll find a positive correlation, you could do a right-tailed test, and your critical value will be easier to reach than it would be in a two-tailed test. But in research studies, people often use the two-tailed test even when they do have a prediction ahead of time. So the two-tailed test is much more common than these other types of tests, because these other types of tests are actually a little bit controversial, because it's difficult for a researcher to confidently say that the correlation can only be at one end of the number line and not the other.